Alright, so today we're going to be going over something called separable differential equations. And these are essentially a special class of differential equations. And once you recognize a differential equation falling into this class, there's a very specific way to go about solving the differential equation and finding the function that has the derivative corresponding to that differential equation. And that's very useful if you had initial value problems that with the derivative that of the differential equation. So basically, a function's differential equation is separable if y prime is equal to f of x comma y. So that's the function's differential equation, can be expressed as dy over dx is equal to g of x times h of y. In other words, as a product of a function of x and a function of y. So essentially, if you were given a differential equation and you can take that differential equation and create two subfunctions out of it, one being a function of x and one being a function of y, then that original differential equation is separable. And this kind of like the terminology kind of like hints at what it is. Like you can separate out the differential equation into a separate equation for x and into a separate equation for y. And if a differential equation is separable, there's a very systematic way of solving for the function with that differential equation. So basically, given that you have d of y over d of x is equal to g of x times h of y, assume that h of y is not equal to 0. So basically, like whatever function that we end up with for y, it just cannot take on the value of 0. That's like one assumption that we make. So if h of y is not equal to 0, then we get 1 over h of y times dy over dx is equal to g of x, right? I'm just taking h of y to the other side. And if I take the integral with respect to d of x on both sides, I get something like 1 over h of y times d of y over dx. And then taking with respect to x, so of that variable, is equal to g of x times dx. Now over here, you can treat it as a fraction because it's inside of the integral. And then I get 1 over h of y dy is equal to g of x dx. And now we've basically ended up with two different indefinite integrals. And hopefully we can find a closed form solution for both of these indefinite integrals. And then we'll get some, on the left side, we'll get some function with respect of some function of y. And on the right side, we'll get some function of x. And overall, and that will give us basically the overall function that led to the original differential equation. So that's the whole idea behind separable differential equations. And let's see now a concrete example. So problem 1. We're given d of y over d of x is equal to 2x times, we're given, 2x times 1 plus y squared times e to the power of x squared dx, or sorry, just e to the power of x squared. Now we can see that this differential equation is separable because we can say like h of x is equal to 2x times e to the x squared, and then g of y is equal to 1 plus y squared. So I've clearly separated out the original differential equation into a product of two different functions, one fully dependent on x and one fully dependent on y. So we have a separable differential equation here. We know that g of y is never equal to 0 because this function is always greater than or equal to 1. So we don't have to worry about the 0 case. And therefore, we can go about using what we showed previously to solve this. So rewriting this as d of y over dx is equal to 2x times e to the x squared times 1 over y squared. I'm going to take all the terms with y on one side, so I get dy over dx times 1 over 1 plus y squared is equal to 2x times e to the x squared. And then, like we saw previously, we will end up with the integral of 1 over 1 plus y squared times dy is equal to the integral of 2x e to the x squared dx. We already know that this is simply the derivative of tan inverse. So this evaluates to tan inverse of y. Now on the right side, to evaluate this indefinite integral, we will need to do a use substitution. And the substitution that seems most reasonable is doing w is equal to x squared. We end up with dw is equal to 2x dx. And then dw over 2 is equal to, or actually we don't need to do that. So we get dw is equal to 2x dx, and we have everything to perform our substitution. So that's the same thing as the integral of e to the power of w dw. And then continuing on this path, the integral of that is simply e to the power of w, and then resubstituting in the value for w, we get e to the power of x squared. So collecting for whatever we have found out so far, we got tan inverse of y is equal to e to the power of x squared. Now we want to get y by itself. We can multiply by tan, or we can multiply everything by or take the tangent of both sides, and we get y is equal to tangent of x squared plus c. Oh yeah, and then we need the plus c over here because, like I said, this differential equation can be valid for multiple functions, and so we need somewhere to put the plus c. And over here in this step, once I evaluated this integral, I put the plus c. You could have put it over here like tangent inverse of y plus c, but it doesn't really matter because as long as you're making sure that you represent it as a constant, it should be fine. And so over here this should have been plus c, and then I took the tangent of both functions. So tangent of tangent inverse is simply getting back the function or the value itself. So I get y is equal to tangent of x squared plus c. And generally we need to make sure that we specify that this function that we just ended up does not take on the value of y equals 0, because that is an important assumption we made when doing this step. And so y is 0 whenever tangent of x squared plus c takes on the value of like 0, pi, etc., right? So you have like 0, pi. So anything of 0 plus 2 pi k, or not 2 pi k, 0 plus pi k, where k is an integer. Those domains are invalid for this function. So basically, whenever e to the power of x squared is equal to pi k, for k being an integer, our function over here, this differential equation, is not defined. And so solving for x, we can take the log on both sides. So we get x squared is equal to natural log of pi over k. And then, so x being equal to the square root of ln pi over k. These are all invalid domain points. So basically, we need to specify that our domain is x is not equal to the natural log of pi times k. And because natural log only takes in values greater than 0, that must imply that k is greater than or equal to 0, or any integer greater than or equal to 0. So those are values of our domain that are undefined for our function that we ended up in. So when we do the step and we find, or just in general, or whenever we're solving for the initial value problem, right, we have to also check back and make sure that our domains are valid. And one thing I did do over here is I just ignored this plus c and just consider it to be 0. But if you want to be perfect and exact, we just need to add this plus c, like c plus e to the power of x squared is equal to pi k is an illegal value, and therefore like our whole analysis would have been like ln of pi k minus c over here, and then square root of ln of pi k minus c, and then x is simply not ln of pi k minus c, and then that would mean that that would mean that pi over k minus c is greater than or equal to 0, and therefore c over pi, so k is all integers greater than or equal to c over, or it should not, or sorry, k is all integers greater than c over pi, not greater than or equal to, because ln does not take the value of 0. So c over pi, and then k is simply any integer that satisfies this. And so this is the more exact version of our problem, because over here we solve for an indefinite integral, but usually you'll know the value of c, and the rest of the stuff that you do over here is just mechanical. So yeah, that was separable differential equations.